Okay, in this video, let's talk about the solutions to ax equals b compared to the solutions to ax equals 0. So this is the 0 vector, right? These are vectors, just do this. And so when b is not equal to 0, ax equals b is called a homogeneous equation, right? So this is, non-homogeneous. A non-homogeneous equation. When ax equals 0, that's called a homogeneous equation. And the question that we are going to address is, if you have a matrix A, okay, then you can look at the system ax equals 0 and solve it. And if you have a non-zero vector B, then you're also going to get a system of equations ax equals b. And the question is, when you look at the solutions to ax equals 0 and ax equals b, how do they compare? Okay, well, there's a theorem that answers this question. But before we get to the theorem, let's look at an example. So let's say that you're trying to solve, okay, let's look at the homogeneous equation, x plus y plus z equals 0, 2x minus y plus z equals 0, 3x plus 2z equals 0. Okay, let's solve this. So we have our matrix A, it's homogeneous. Okay, so let's just set up the augmented matrix. It's going to be this, right? Okay, and of course, since it's a homogeneous equation, when you do the row operations, the last column, the constant, whatever it's called, vector of constants, it's always just going to be 0, 0, 0. So you could just leave it out, but let's just leave it in, just to emphasize that we're talking about a homogeneous equation. Okay, let's row reduce this matrix. So again, when we're talking about row reducing the matrix, we're row reducing this, we're row reducing that, right? That's our matrix A. Our matrix A is, okay, 1, 1, 1, 2, negative 1, 1, 3, 0, 2. That's our A. Okay, let's just put a little cloud. Okay, let's row reduce this matrix. So what are you gonna get? Let's see. Well, we're gonna do row 2 minus 2 row 1. So that'll give me 0, negative 3, negative 1, 0. And then we're gonna do row 3 goes to 3, row 3 goes to row 3 minus 2 row 1, right? Oops. So I should say R2 goes to row 2 minus 2 R1, row 3 goes to row 3 minus 3 row 1, and I'm going to get 3 minus 3 is 0, 0 minus 3 is negative 3, 2 minus 3 is negative 1. And then, I'm going to change row 3 to row 3 plus row 2, right? That's our last step. Right, the first column is done, it's perfect. And then when you look at the second column, just to review how it works, when you look at the second column, I have this. And so my second pivot is going to be a negative 3, and I want this number below it to be 0. So I'm going to get 1, 1, 1, 0, negative 3, 1, 0, 0, 0. And now my matrix A is it's not A anymore, it's the echelon form of A. And we can continue. We could do back substitution by writing out the equations, but let's just get it to reduced row echelon form. So let's make all the pivots 1. So we should divide row 2 by -3, right? So row 2 goes to -1/3 row 2. Okay, I'm going to get some fractions. And then the last step is to get everything. So I have these pivots. My pivots are now 1, and I need to get everything above the pivots to be 0. So this 1 on top, that needs to go to a 0. So the last step is to do row 1 goes to row 1 minus row 2, right? So I'm going to get 1, 0, 1 minus -1/3 is 4/3. No, did I do that right? Oh, sorry, there's a -1. There's a -1 here. So I'm going to get a +1/3 here. Oops. Okay, so I'm going to get 1 minus 1/3, and that's going to be 2/3. And then 0, 1, 1/3, 0, 0, 0, and then 0, 0, 0. So now this matrix A, well, it's the R ref of A, right? This is the R ref of A. And now it's really easy to just write down the solutions. So when you write out the equations, it's x plus 2/3 z equals 0, y plus 1/3 z equals 0, right? My pivot variables are x and y. I have a free variable, which is z. So you set z equal to any constant, say z equals t. And then when you solve for x, you're going to get -2/3 t, and you're going to get, when you solve for y, you get -1/3 t. So the parametric form of the solution to the homogeneous equation, this xyz, is t times, okay, -2/3, -1/3, 1. Okay, so that's the homogeneous, that's the solution to ax equals 0. And, you know, this is a shorthand. This is saying for any constant t, right? So I have infinitely many vectors, one for each of the infinitely many values of t. Okay, notice again that if you set t equal to 0, you just get 0, 0, 0, right? This is good because the homogeneous system always has the 0 vector as a solution. All right, so that's our ax equals 0. Now let's compare that to the solution to ax equals b, where solution to ax equals b with b equal to the vector, okay, what's the vector I want? 3, 2, 5. So now we're solving ax equals b. Where is, oh, I guess I could copy and paste, but I'll just write out a over again. Okay, now it's the same process, right, of getting the reduced row echelon form. Now, if you think about it, the reduced row echelon form, right, what I'm going to get with these 3 columns when I reduce, it's going to be exactly what I did before, because you're just going to get the reduced row echelon form of A. But the numbers 3, 2, and 5 are going to change. It's not just going to be like 0, 0, 0 all the time, as it was for the homogeneous. So I'm just going to write down what you get and skip all the steps because it's the same procedure. You just want to make sure that you do the steps to the vector b, and you're going to get 1, 0, 2/3, 5/3, 0, 1, 1/3, 4/3, 0, 0, 0, 0. Okay? So that's all we have. And then when you write out the system, so again, you just write out the equations, right? X plus 2/3 z is 5/3, y plus 1/3 z is 4/3. You set z equal to t, you solve for x, y, and z. You're going to get x, y, z equals 5/3, 4/3, 0 plus t, negative 2/3, negative 1/3, 1. So that's the solution to the non-homogeneous equation. Now let's compare this solution. So this is the solution to ax equals b. Okay. That's the general solution. Notice that when t is 0, you're just going to get 5/3, 4/3, 0. So that's a solution to the non-homogeneous, right? So this, notice the pattern. This is a solution to ax equals b. Right? That vector is one solution to ax equals b. And now notice that this part, right, this t times negative 2/3, negative 1/3, 1, that was the homogeneous solution. That was the solution to ax equals 0. So what we see is that this solution to ax equals b, this solution to ax equals b is, it has the form, a solution, right, one solution to ax equals b, let's just, okay, plus, right, that plus, the homogeneous solution, the solution to ax equals 0. So let's just draw a picture of the homogeneous solution and the non-homogeneous solution. So the homogeneous solution, okay, here's the x-axis, positive y-axis, positive z-axis. The homogeneous solution is all multiples of the vector negative 2/3, negative 1/3, 1. So that might look like, okay, negative 2/3, negative 1/3, 1. Maybe it's something like this. So that's the vector, and then all scalar multiples of this. And it's a line through the origin, right? A line through the origin. That's all the vectors on this line. Those give me the solutions to ax equals 0. So that's the solution to ax equals 0. And ax equals b is, see, it's this line, right? This line, but then plus 5/3, 4/3, 0. Well, what do you get when you take a line and then add a vector? You get a line that's shifted by that vector. So for instance, if you take 0, 0, 0 here, and then just add 5/3, 4/3, 0, you're going to get 5/3, 4/3, 0. And similarly, if you take any other vector, okay, let's do a different color. So let's put this solution in blue. Right, you're just translating by this vector negative 2/3, negative 4/3, 1. All these vectors are just going to get translated by that amount, and what you're going to get is this blue solution here. So that is the solution, the general solution to ax equals b, the non-homogeneous solution. So in this example, the solution to ax equals b is also a line that does not go through the origin, right? Let's just write that down. Line not through the origin. And the solution to x equals 0 is a line through the origin. Okay. So this example is actually representative of the general situation, no matter what your A is and what your B is. Well, first of all, if ax equals b has no solution, then there's just no solution. But if there is a solution, if ax equals b does have a solution, how it's gotten is you take the homogeneous solution and it's always a shift by one solution to ax equals b. So let's write that as a theorem. Okay, so we're ready to state the general theorem now that we've seen an example of what we expect. So the theorem is, okay, suppose that ax equals b is consistent. Right? So suppose it has a solution. Okay. And let xp be one solution to ax equals 0. Then the general solution to ax equals b is the set of vectors of the form y, okay, let's use x. X equals xp plus xh, where xh is a homogeneous solution. So in other words, one way to think about this is that the solutions to ax equals b, okay, the general solution to ax equals b is, okay, it's xp, so that's one solution or a particular solution, to ax equals b, okay, plus all the vectors that are solutions to ax equals 0. So it's the solution to ax equals 0. And let's put that in the box. So this is the example that we did before. That's an example of this, right? This 5/3, 4/3, 0. I mean, if you just plug it into the equation, you'll see that it's a solution to ax equals b. And then you have this homogeneous part, the green part, the solution to ax equals 0. Right? And one way to kind of see it is just from doing the solving. I mean, you can kind of see that when you do this example, you're going to get this out of the homogeneous part. It's going to just kind of come out of the mechanics of the solution. But let's see it in a more maybe abstract, maybe conceptual way. So let's take the proof of this. So first of all, let's check that whenever you have a vector of this form, so suppose that xp is a particular solution to ax equals b. Let's check that when you add a homogeneous solution, right, add a vector that's a homogeneous solution, you don't actually change the fact that you have a solution to ax equals b. So suppose that xp is a particular solution to ax equals b, and xh is a homogeneous solution. Okay, what happens if you do a times xp plus xh? So you take a homogeneous solution, you take a particular solution, you add them together, you get xp plus xh. What do you get when you do a times that vector? Well, by the linearity of matrix vector multiplication, this is going to be a times xp plus a times xh, right? And what's a times xp? By definition, it's the vector b. And what's a times xh? it's the vector 0, right? The 0 vector, and b plus the 0 vector is b. So therefore, if you have one solution to ax equals b, okay, and you have a homogeneous solution, you can produce more solutions to ax equals b. You just add the particular solution to the homogeneous solutions. Okay. So whenever you have a vector of this form, xp plus xh, so xp plus xh, this is a solution to ax equals b. That's just part of the theorem, right? We also have to prove the converse. So conversely, suppose that you do have a solution x. Suppose that x is a solution to ax equals b. Okay, maybe we shouldn't use, okay, let's use x0. Suppose that x0 is a solution to ax equals b. Why is it true that x0 must have the form xp plus xh? Well, the reason is that, let's consider the vector x0 minus xp. Okay, what do you get when you do a to it? So a times x0 minus xp, by the linearity again, that's a times x0 minus a times xp, right? Well, a times x0 minus a times xp, what's that equal to? What's a times x0? B, by definition, right? x0 was a solution to ax equals b, and what's a times xp? That's also 0, that's also b, right? Because xp is a solution to ax equals b, and what's b minus b? That is the 0 vector. So what does this equation, well, right? What we showed was that a times the vector x0 minus xp is the 0 vector. Therefore, okay, therefore, x0 minus xp is a homogeneous solution. Say xh. Let's call that vector xh. Then, okay, you just add xp to both sides. x0 is xp plus xh. Right, and x0 was an arbitrary solution to ax equals b. So what we showed is that any solution to ax equals b is going to have this format xp plus xh. It's a homogeneous solution plus a particular solution. Okay, so let's say that you have some matrix A and you solve ax equals 0 and you get a plane. So let's say that ax equals 0 is a plane. Well, if ax equals b has a solution, right? Let's say that b is a vector for which ax equals b has a solution, then the solution to ax equals b must also be a plane. And similarly, okay, in this example, when we solved ax equals 0, we got a line, right? Then if ax equals b has a solution, so let's say your b, makes it so that ax equals b is consistent, then that solution must also be a line. So it's not possible for you to have the solution to ax equals 0 be a plane, but somehow when you solve ax equals b, you get a line. That just doesn't happen, okay? Yeah. So in particular, let's just think about what happens. Okay, so that's the end of the proof. So in particular, let's say that ax equals 0 has only the 0 vector as a solution. Has only the 0 vector as the solution. Okay. And this happens whenever happens when you have linearly independent columns, when the columns of A are linearly independent. So if Ax equals 0 has only the 0 vector as the solution, then Ax equals b, then no matter what b is, for any b, okay, Ax equals b has at most one solution. Okay, why is that true? Because Ax equals b is either consistent or it's inconsistent, right? That's just true across the board. Now, if Ax equals b is inconsistent, that's just the same as saying there's no solution, right? If Ax equals b is consistent, so it has a solution, the fact that Ax equals 0 has only one solution, that means that Ax equals b would only have one solution, right? So in general, the number of solutions, I mean, the shape of the solutions to Ax equals b, provided that the system is consistent, is just the same as the shape of the solution to Ax equals 0. Okay. So for instance, suppose that Ax equals b, let's say that there was a b for which Ax equals b has infinitely many solutions. Then that would imply that Ax equals 0 has infinitely many solutions. Okay. And you know, what does this say in terms of the free columns of your echelon form? So notice that in this case, your A, there were two pivot columns and there's one free column, right? So these are the pivot columns, and there's that column is the free column. And the fact that there was one free column told you that, see, you're going to get one free variable, t, right? One free variable. Because there's one free column. In general, the number of free columns will be the number of free variables. And that will determine the size of the solution to Ax equals 0. So for instance, here there's one free variable. And so your solution is like one variable times a vector. So you get a line when you do that. Okay. So if Ax equals 0 has no solutions, then that's really the same as saying that there's no free variables, and that turns out to mean the same as the columns being linearly independent. Okay, that might be farther into the course, but that's just a preview of what's coming. Okay, so what are the main takeaways of this video? We were talking about, right, Ax equals b for b not 0. That's a non-homogeneous equation. Ax equals 0 is a homogeneous equation. We looked at an example and we saw an instance of the general theorem, which is that the solutions to Ax equals b, provided there are any solutions to begin with, they're just translations of the solutions to Ax equals 0 by one particular solution to Ax equals b. Right? It's just xh plus xp. And one thing to think about is, if you look at this example, our xp was 5/3, 4/3, 0. That's your xp. Right? And then any like t times that vector, that's your xh. Any t times this vector is your xh. Now suppose that you had a different xp. Right? Suppose that you had a different solution to Ax equals b. Well, it turns out that the xp plus xh's will still be the same. And that would be sort of interesting to think about. So if you translate the green line by this xp, this red vector, you get the blue line. It turns out that if you take any solution to Ax equals b and then translate the green line by that vector, you still get the same blue line. Okay? That's really what the theorem is saying here. Okay, so that wraps up the video. Thanks.